messing up. And the other one, most people got it right. And I think I see why. So I'm going to go over the first, or this is quiz A. Now I put the solutions up if you look on OneNote, they're there. For quiz A, it was straightforward. And I had a source here of plus or minus 3 e to the minus 3t u of t. And then I had a resistor here, R. And then I had a resistor R here and a capacitor here. And I wanted the voltage here, plus the minus, I called it y of t. And the value of R and C were 2. So for this one, what I'm going to do is try to go through this with you. And this is the way I do it. And there's many ways to do it. But what I'll do is I just call whatever the resistance is or impedance on the output, I'm going to call that just ZRC. So it's a capacitor resistor in series. And then I know the impedance of the capacitor is 1 over SC or CS, right? Now with that, I'm going to just take that as ZRC, put it here. And that's equal to 1 over R plus CS, because it's 1 over the first impedance plus 1 over the second, correct, class? Mm-hmm. Then I take that, and now I'm going to go ahead and just leave that alone. And now I'm going to say, if this is ZRC here, my transfer function, and that was the homework on transfer functions, H of S is equal to the output impedance ZRC over ZRC plus R. Now that H of S is, of course, V out of S, or in my case, Y, but I'll just call it V out of S over V source of S. Do you all see what I'm doing here? Could I have a show of hands to make sure everybody understands what I'm talking about? Transfer functions are just output voltage over input, right? It's voltage division. Do you all agree with me here? Mm-hmm. I got to make sure everybody's clear on this, because this was not a hard problem, but people mess this up. So when I take a look at this, I can say that I divide top and bottom by ZRC, and I have 1 here plus R divided by ZRC, right? Everybody with me on this? And once I do that, what do I get? I'm doing it this way for a reason, so you see it. I get 1 plus, then I have R divided by ZRC. Well, that's ZRC. 1 over that is going to be just 1 over RC plus CS. Does everybody see this? Doing it to make sure you see this. It's a trivial problem, but you can get tricked in the weeds here when you do all sorts of weird analysis. This is not hard at all. Are you all with me? You see it? You're getting your mouth up. Do you see it or not?
Where did the C and RC come from?
Right here. Right? That's the impedance. If you have 2 in parallel, it's 1 over the impedance of the first plus 1 over the impedance of the second, right?
Yes, so how is it 1 over RC plus C then?
Well, I'm sorry, this is 1 over R.
Oh.
My bad. 1 over R. I am so sorry. Yeah, you were right. Are you with me on this, class? Mm-hmm. Now, at that point, I'm going to multiply through by R through here, and I get 1 over 1 plus 1 plus RCS. And I'm doing this on purpose slowly. Everybody got that? Mm-hmm. And then what I do is just replace this with 2. Right? Now, R times C is 2 times 2 is 4, correct, class? Mm-hmm. So I'm going to divide top and bottom by 4, so I just have the coefficient of S as 1. Everybody got that? So when I divide by 4, I get 1/4 on top, and I get 1/2 here. That's the transfer function H of S. Next, I need the transfer function for this. That's simply going to be the magnitude 3 over 3 plus S. Does everybody follow me on that? Got to make sure everybody sees this. This is not meant to be tricky. It's just means you go through it methodically. Now, here's what I think people did. They tried loop analysis. They tried some kind of, you went overkill on me. I mean, this is a simple problem. It's voltage division. It's not, you don't need to do Thevenin equivalent or mesh. No, you can do it with nodal if you want, but honestly, people went beyond the Call of Duty and got into a mess. These are trivial problems. These are not hard at all. Now, when you do this, V out of S is going to be what? Or Y of S Well, that's h of s times the input, the source of s, right? I'm putting it just in general terms. Now, I plug in the h of s. H of s is right here. So I have, this is equal to 1/4, right? Divided by 1/2 plus s. And it's times v of s, which is 3 over s plus 3. Does everybody see that, class? All right, gotta make sure you do. And there's some people who are coming here, and they should, because I have a feeling if they start to blow this class off, they're gonna pay for it in spades coming up very shortly, because you gotta realize something. This stuff is all builds on previous lectures. And like this analysis, you can't do without understanding Laplace transforms. You're gonna see you can't do a lot of stuff unless you understood the prior lectures. You've got to really, like right now is the time to really dig in deep here, or else you're gonna be in a world of hurt. All right, now I'm gonna just put this as 3/4 here. Agreed? And now break it out. I have a over s plus 1/2 plus b over s plus 3. Y'all agree with me? Now it's the simple partial fraction. People even mess this part up, which gave me a little concern. This is not meant to be tricky. This is as simple as it gets. On tests, the problems will be harder. All right? They'll be quadratics or something. They're not going to be this simple. You'll have to complete the square. You're going to have to do more with them. You'll notice that these are simple first order equations. There's either an R and a C or an R and an L. There aren't an RLC. RLCs are more involved. I'm just telling you that right now. So when I take a look at this, to get A, I simply cover this up and I evaluate everything remaining when S is minus 1/2, correct? When it's minus 1/2, right here, right, what do I get? Well, 3 is really what? 6/2, right? Right? 6/2 minus 1/2 is 5/2, correct? So I'm going to have A is going to be 3/4 over 5/2. And I'm doing it on purpose this way. And then when you take a look at this, what does it come out to be? And when I take a look at this, I'm going to go ahead and multiply top and bottom by 2. And I'll just put it here. Let me do it this way. So I'm going to have, it's going to be 3/4 divided by minus 1/2 plus 3, and that would be equal to 3/4 over 5/2. So top and bottom by 2. That's 6/4 over 5, and that's 3/2 over 5. That's 3/10. I'll leave it as that. So A will be 3/10. Yeah, I believe that's right. And then for B, to get B, I cover this up and I let S equals minus 3. And then for B, I'm going to get 3/4 over 1/2 minus 3 here. That's 3/4 over, and that's minus, wait a second. Did I do that right? Yeah, and then this is going to be, six, well, it's the way I'm going to do this, try to do this in a way. This is really going to be 6/2 minus, so it's going to be minus 5/2, right? Correct, class? Yes. Pardon me? I mean, I'm just doing it this way. And you go ahead and, for this one, it's going to be minus, and that's going to be, wait, just do it this way. Minus 3/10 there, right? Is that right, class? And I want to make sure about one thing. Yeah, that should be right. So that's going to be minus 3/10 here. And that means when I take this to the other domain, then I'm going to get this. So it's 3/10, and it's going to be e to the minus t over 2 u of t minus 3/10 times e to the minus 3t u of t. And the trick was to make sure that you did this transfer function right, if you're going to do it that way. How many had this one? All right. Y'all, I mean, did you all do it this way? Did you try nodal or something? I saw a weird analysis. I couldn't tell what was going on here. But this is the simple way to do it, and you should have gotten it. The next one was it was a straight, this one was easier in my opinion, but it was a simple u of t function without any exponential multiplying as a source, and it was, come on, see, the one you had was this. It was a source here that was just plus to minus 5 e to the minus 3t. No, I'm sorry, there was no, it was just u of t on yours. And then there was a capacitor here. And the capacitor was 1/4. And then there was a resistor here. And the resistor here was 2. I believe this is the right one. And this was the output, V out of S. That's what, or V out of T is what they wanted. Do you all remember this one, class? So this is V out of T, actually. All right. Admittedly, this was easier, so the grading is going to be adjusted because of that. So when you take a look at this one, this is just 5 over S. Do you agree with me there? 5 over S. This is going to be 1 over SC, so it's 4 over S. Agreed? That's just R, 2, period. You can leave it as 2. Now, when I take a look at my V out of S, it's the transfer function. The transfer function is equal to 2 over 2 plus 4 over S. That is the transfer function H of S, times the input voltage, 5 over S. Does everybody follow me on that one? I want to make sure you do, because what I'm doing is just taking the transfer function times the input voltage. The transfer function is always the output divided by the input. And the input here is the voltage source. How many see this right here? Regardless if you had it or not, right? All right, now, when that S is multiplied through, what happens? That goes away, and this becomes 2S, right? Agreed? Then we simply take a look at that, and that's 5 times 2 is 10, right? But actually, I should just leave it like this, because now what I'm going to do is divide top and bottom by 2, and when I do, that becomes 2, and that goes away, right? And that's straightforward, because that's just going back to the time domain. That is in the simplest form, right? It's a simple pole, and this goes right back as simply 5 e to the minus 2t u of t, and that was the output voltage for that one. Now that one was admittedly easier. What I was supposed to do, unfortunately, didn't come out. This is supposed to be actually 5 e to the minus 3t u of t, all right? So I didn't have that exponential there. But is everybody clear on this stuff? Remember, the problems I give you here, they're going to be simple voltage division, really, times, I mean, that kind of a problem. In a quiz, it's never going to be over the top hard. It's always fairly straightforward, fairly easy. And don't make it harder than it is. Now, on tests, you may have to use nodal, but you'll have more time. Okay. All right, any questions about that at all? All right, today, any questions about the homeworks at all? Yeah?
4.42.
What is it? Just tell me.
It's you got a voltage source on the left side.
Tell you what, which problem is
4.14.
4.3?
4.14.
14. All right, hold on. You're able to observe, see the solutions too? I'm just making sure. All right, oh, that's a good problem. So this is going to be R1L and R2. So they have R1 and then L, right? And then R2, that's R1, R2 here, right? And then they have a voltage in here that is given as a waveform. Now, help me out here, does it?
It's a 0.
It's 0 and it goes to 1, it has a height of 10. So it does this. That's 10, like so, and that's 1 right here. And this is V of t, correct? We'll talk our way through this one. The big thing is, what do I do with that? Well, you construct it based on known functions. So my V of t here, V source of t, would be equal to, well, how would you make this? How about we say 10 u of t? That turns it on, right? Now we want to turn off right here. So what if we go minus 10 times u of t minus 1? Everybody agree with that? That'll replicate that. We could do it with a pulse function, but this will do just fine. Do you agree with me there? Now when you take the transform of this, what happens? Vs of s becomes what? Well, the first one is just 10 over s, right? What about the second one, time delay? What happens? Minus 10 times what? It's over s, but then I have a phase of e to the minus s here, don't I, class? Do you all agree with me? How many understand that? Whenever you have a time delay, it brings in a phase right there. The phase change, e to the minus s times the time delay. Correct, class? And you can look this up, but you need to be familiar with these. Now, so I've got this transform. Now what about this? I actually want the current. So I want I think it's IR, right? The 2 of t, right? Isn't that what they want in the problem? Correct? All right, now your transfer function is a little different. Now my transfer function here is not a voltage. H of s is equal to I R2 of s, I'm going to put a capital I R2 of s, over the source voltage, Vs of s. That's the transfer function you want, correct? With me on this? All right, well, you can do this several ways. Now, I'm going to tell you right now, there is no one best way. But what I would do with this one is this. I would say, this is just me personally. You could solve, does he do it with nodal in the book? I don't know how he does it. Current division is what I would do too, and here's why. I'm going to get the total current here in the S domain. Once I have that, then I multiply by the current transfer function, all right, the ratio. So I'm going to get this total current first. And that total current, I total of S, is going to be what? Well, it's this voltage, V of S, right? Divided by the total impedance, correct? And here's where I do the old trick again. I'll say that this whole thing is going to be one impedance. And I'm going to say this ZRL here is going to be 1 over R2 plus 1 over LS. Y'all get me what I'm doing here? They're in parallel, correct? So I'm doing it this way. Now again, you're used to multiplying, you're doing the product over the sum a lot of times, but I like the 1 over things because it's easier for me to deal with here. Y'all got with me on this? Now I'm going to try to clean it up a little. So first, I'm going to multiply everything by S. So I'm going to get an S here, I'm going to get rid of the S here, right? And then put an S on top. Are you with me? Now I'm going to go ahead and multiply everything by R2. So when I do that, I have R2S over S plus 1 over L. Y'all? I'm sorry, R2 over L, my bad. All right, now, at that point, if you want to put values in, what are the values? Are they weird or? What is R2?
R2 is 2, and then L is 1/3.
All right, so if this is 2, I'm gonna just go ahead and put it in. That's the number I can deal with. And L was 1/3?
Yes, that's.
So it's 6? Okay, that's fine. Now, I'm ready to go ahead and get I of S here because I've got my Z of S, right? That's the input impedance. Y'all, oh, sorry, I don't have the input impedance yet. I have to add R1 to it, my bad. Are you with me, class? So now I can say my Z in, the input impedance in the S domain would be, what is R1?
1.
Just 1. All right. 1 plus 2S over S plus 6. Agreed? And if you want, you can do this to make it nice and easy. Well, I want a common denominator of S plus 6, so I'll say S plus 6 here, and then I'll multiply top and bottom right here, S plus 6 over S plus 6. So I have S plus 6, right, plus 2S is 3S plus 6. Do you agree with that? So this is 3S plus 6, and I'm going to write this as 3 times S plus 2 here over S plus 6 here. Agreed, class? And that's my Z in of S. I'll slow down here. Okay. That's the input impedance right here, from here over. That's Z in of S. Now, to get I of S, I take V of S over Z in of S. Do you agree, class? Follow me on that? Well, I've got V of S right there. So now I have 10 over S. And really, I can go ahead and say that's 1 minus e to the minus S is times that. Correct, class? I can take the 1 over S out. Correct, class? That's the V of S. Then it's divided by this. Well, if I divide by that, I flip it and multiply. So now I have this times S plus 6 over the quantity 3 times S plus 2. Everybody agree with that? Now remember, that's in the S domain. I should make that a little clearer. So now I have this right here. That's 10 over S here. And if you want to, you can make it 10/3. It's probably better to do that. Agree, class? Now I need to do that, and I have to take, that's the input current in the S domain. To get that current through there, I have to do current division over here. Correct, class? By the way, this would be what? S times L, and L was 1/3, did you say? So this is S over 3 right here. Correct, class? I mean, yeah, that's right, the impedance there. Now, if we do current division, I'll slow down here. If I want the current here and I have the net current coming into the pair in here, these two, then I take the opposite impedance over the sum of the two times the incoming current. Do you agree with that? Do you all remember current division? All right, so I'm going to say now my IR2 of S is going to be the total current, which is going to be that right there. So let's keep me straight on this one. So I have 10/3. Then it's divided by S. Then it's times S plus 2, right? Then there's an S plus 6 on top. And it's times 1 minus e to the minus S here. And that's an S. And I'm going to take that and I'm going to multiply it by the opposite impedance, which is this, S over, it's going to be times S over 3 over the sum of these two. And R2 again was 2. Just put in a 2 there. So now it's going to be S over 3 over S over 3 plus 2. And that would be I of S. Do you all agree with me here? How many see the way I'm doing it? Did you try it this way, by the way? I mean, it's pretty straightforward. If you think about staying in the S domain, if you did these problems like circuits problems, how do you always do problems like this? Well, you could use nodal or mesh, right? And that's doable, and it's very allowable. But here, if you wanted to do a current division, you first have to find the total current, so you have to find the total impedance seen by that source voltage. then divide the voltage by the total impedance. After you get that, you got a current going in here, then you have to divide the current into the component you want the current through, right? And that's the way you did it in circuits, if you asked you to use current division. This might be easier with nodal, to be honest with you. I think it is. Did you do it with nodal? Much easier?
It's a lot easier.
All right, well, if you come here, now there's going to be some cancellation, I suspect. If I look at this, do you all agree I have to multiply top and bottom by 3 to get rid of that S over 3 thing? So if I do that, that's S, that's 6, right? And that goes away. So now I have S over S plus 6, right? Correct, class? Please just watch. Here, there's some cancellation. You see the S plus 6 goes away? So I'm gonna do it right here if you don't mind, because I'm trying to not waste all of this time on here. So now we have that, right? What's the next thing that cancels? S cancels, so we get rid of that whole thing, we get rid of that. Now I'm left with this, correct, class? Now we expand that. I don't know if he did it this way exactly, but this is basically how I would do it. So now I can expand this, and I have 10 over 3 over S plus 2. And then I'm going to have minus 10 over 3 e to the minus S over S plus 2. You agree with me, class? Now, this is one of those, when you see that, you always think time delay. Anytime you get that, you always think time delay. This one's straightforward. That just goes to what? 10 over 3 e to the minus 2t u of t. Check that box. The next part is what? Minus 10 over 3, right? Now, forget that for now. If it's just this, what is it? E to the minus 2t u of t, right? But with this, there's going to be a time delay of 1. Correct, class? Does everybody know what I'm doing here? Right? Because we know that that's a time delay. And just to be clear about this, if I have x of t goes to x of s, then x of t minus tau goes to e to the minus s tau x of s. It's just that phase form. I call it a phase, really, because when s is j omega and there's no real part, it is representing a real phase. So this is going to be e to the minus 2t minus 1 u of t minus 1. Is this the form of the solution he has in the book? You know? Is that it? I mean, I'm asking for a reason, because if he used a pulse function, he may have had a pulse function come out or something different. But he used this one? Okay. Got that? That's a good problem, by the way. Next, any other questions about the homework? If you're keeping up with this homework, please, I encourage you. If you fall behind now, it gets overwhelming. I mean, some of the stuff with foyer especially, you'll be so confused you won't know which way is up. So I'm really encouraging you to stay up with the homework right here. Any other questions about Laplace transforms? One thing I'm going to tell you, anytime you have Laplace transforms where you have a Ks, or some constant, Ks plus, say, well, call it C1s plus C2 over, and say you have S plus a, let me do it this way. Yeah. S plus, or S, yeah, plus a squared plus omega naught squared. When you have two factors up here, now you have to break this out into two portions. You're going to have, and well, that isn't exact. It's almost an exact transform, but for this one, actually, you would want an S plus A here. Do you follow me on this, class? Because you want an S plus A to fit the form of a cosine, an exponential cosine. So what you would actually do, factor out the C1 right here, and then see if that matches that A. And if it doesn't, then you would have to add or subtract something from it to make it match. And that would mean you would get a constant outside. I'll spend more time when we get to the quadratic, this in the actual circuit solutions, all right, and showing you some tricks that I can't really explain well until you see the problem, but I will. And you basically done the circuit problems, the transient problems, where you put in the voltage source or current source. Or really, it's voltage. I wanted you all with voltage sources, right? All right. So now for today, what I'm talking about is operational amplifiers. and I'll slow down. How many have had operational amplifiers? Good. I'm talking. Everybody should be interested in this. You know what an operational amplifier is? It is, godsend. It's the best circuit in the world for you because it's an amplifier that does exactly what you want very easily. You haven't had analog, have you? Okay. Well, it's a black box of sorts, and what's beautiful about this thing, most operational amplifiers can be viewed as ideal op amps, and the laws that govern them are trivial, but people mess this up because they try to look at, I call them cookbook solutions. They go online and see, this is the solution for this one, and they fail to understand that unless they understand the first principles, I can change that circuit or a circuit can be modified and they'll never get it. So first, what is an operational amplifier? Just put down op amp. Really, this should be in your electronics courses or in Dave Irwin's circuits course, but we're going to do it here. Now, an operational amplifier looks like this. It has an input, it has a negative and positive terminal here. The negative is called the inverting, and the positive is called the non-inverting terminal. And it has an output, V out. This is V minus, this is V plus. That's input, that's output. Now, there are a lot of other things I'm not showing you. For instance, that's a triangle. There's a power source. There's usually a plus and minus voltage source that's driving this, all right, that they don't show. The only thing you deal with, and put ideal down here, this means there's no leakage current or anything. There's no trickle current. So here's what the laws are. If there's a current, I just call it I minus, call this I plus. Now here are the laws. There's only two of them. The first is I negative is equal to 0, I positive is equal to 0. No current can flow in and out of the negative or positive terminals. The next thing is this. If the difference in voltage, V minus V plus, is 0, there can be no difference in voltage. Now naturally you're going to say, well, how can that happen? Well, it's done by electronics in here and things called differential amplifiers and things beyond the scope of this class to discuss. You're going to have to take that on faith. That happens and it works that way. So let's go through a simple operational amplifier problem and go through an analysis. Again, you don't know everything that's here. You just know the black box approach. So suppose I put a resistor here, R1, right? And now I put a voltage source here, and I'll just call that V in. We're not even going to the estimate yet. Ground that. Now I'm going to put the positive input, I'm going to ground. Then I'm going to put another resistor here, and I'm going to call that R2. That's my V out. All voltages, if they're just dangling like that, are referenced with respect to ground, and ground is 0 volts, isn't it, class? So they always assume, if you just see that, it assumes it's referenced to here. That would be the minus terminal. And the ground is always 0 volts. Now, let me go through this with you and show you how this works. Because there's some natural questions and there's things that irritate you. All right, the way we always start this, or you should have in the first, when you're doing this, you always find the voltage across one of these terminals. The minute you got the voltage on one of them, you got the voltage on the other. You all follow me on that, class? There can be no voltage difference. So if that's 0 volts here, what's the voltage here?
0.
All right, agreed? Now, the next thing you take a look at is what does that do to the circuit? Well, if there's 0 volts here and there's VI here, what's the current here? Call it I1. Well, isn't it always the voltage on one side minus the voltage on the other side divided by resistance, right? That's VI minus 0 over R1. So it's just VI input over R1. That's the current. Follow me? Now, what's the second law? Well, it's first law, is that way I put it. I said no currents into the negative terminal. How much current flows in there? None. Where does all the current go? This way. Follow me? It has to. It can't go into the negative terminal. It has to be routed through that resistor. And it can flow into the input. It can flow this way. That's allowed. Right? but it can't flow into the input. Got it? By the way, the input is a simple, it's basically an FET, a field effect transistor, CMOS. You have CMOS right now, don't you? Don't you have Dr. Newton? Hasn't he gone through?
Yeah, we haven't talked
Who?
about it.
We haven't gone
talked
through
about
it yet.
Oh, all
We're
right.
getting there.
Well, you know what a capacitor is, right? How much DC current can go through a capacitor?
Zero.
None, right? It's an insulator, correct? An ideal insulator. Same with these things. FET is basically the gate, the driving voltage on that thing is basically a capacitor input. So just, I'll spend more time with this later, but I wish you had your device courses first because then it would make a lot more sense. Now, if I take a look at this, what's the voltage developed across R2? It's the current flowing through R2, I1, right? Times the resistance R2. Or the voltage here would be VI times R2 over R1. That's the voltage from here to here across it. Do you all see that, class? Can I get a show of hands to make sure everybody sees? You see in the back? Over here, guys? And I'm doing my best to try to make this simple. Now, if that's the case, what's the output voltage, VI? Now, just watch this, and this is the way you get output voltage. Dave Irwin, if you had him, you were lucky. He's the best circuits teacher in the world. He always, I taught that class with him jointly. The way you always get voltage, that I do, you start at ground like that. This is with respect to ground. Start at ground, and then go to the positive terminal and see what it is. Now, you see that's zero, right? There's no change from here to here. It's still zero, right? But what happens? That's a positive to minus VI over R2 over 1. That's a voltage drop, isn't it? It becomes minus, and it would be Vn times R2 over R1. And then they talk about something called the voltage gain, AV. Amplification of the voltage is really what it stands for. A is amplify, and it's the amplification of the input voltage. And that is simply equal to V out over Vn. Well, if you divide that, you get minus R2 over R1. And this is called an inverting amplifier. Because the output is scaled by R2 over R1 in terms of its magnitude, but it's inverted. So if you had a positive going sine wave coming in, you're going to have a negative going sine wave coming out that's multiplied by the ratio of R2 over R1. Now y'all see, in this circuit, isn't that the simplest amplifier you can think of? You haven't had your courses where you built them. This is trivial, 2 resistors, and I pick them, and I got the range of amplification. Typically an operational amplifier, the first time you use them, MEs use these a lot as sensors. Now almost any sensor that you're going to run into takes some kind of a mechanical or thermal input and changes it into a voltage. For instance, a transducer like a microphone takes sonic vibrations to displace a cone. That has a little coil, and as the coil goes through around a magnet, it induces a current and voltage in that, and that is the thing that would be as the input to this. Then it has to be amplified. Now remember, the input impedance of this, and this is a lot down, this is down the road, you can make this thing to be something where basically, by the ratio of resistances, because the resistance, input resistance here is basically extremely high. You can make R1 100,000 ohms, for instance. Follow me? Once you have that, no current flows into that effectively, all right? But that's another thing. Anyway, this is usually the first stage of amplification in a power amplifier. Now there's other stages that come, and they don't have to always be op amps, and I can't get into all that. But this is the simplest and the first stage of amplification for most low frequency circuits. By that, less than maybe 2 or 3 megahertz. Once you get higher than that, some things change. It gets a little more expensive, a lot more expensive actually, for some of the higher frequencies. And I don't know the actual frequency break range, so don't quote me on that. But I know when you're getting at gigahertz frequencies, it's not quite this simple, because I work on radar, and that's the frequencies I work on. That's a simple one, right? Let's do another one, because if I can go through some permutations of this, you'll see how this works. All right, the next one I'm going to talk about, remember the rules for op amps in place. You know, really, I'm surprised you haven't had op amps yet. Are there any people here that, have you ever built any kind of electronic equipment at all? Sort of? You have? Well, you probably do. I mean, see, nowadays it's hacking. It's all get on the keyboard, do something with your computer. But back in the day, when I was around, we were always building stereo equipment, things like that. Well, I mean, that was the real, that was of interest. Nowadays, I guess it's all your online social media tools and, I don't know, big data, data mining, trying to figure out what everybody's doing, taking out a caucus or two. I mean, well, I don't know what happened over there, but anyways, your focus is different. This is where your focus needs to be right now. So now let's try this. Got a negative or positive here. Now I'm going to do this. I'm going to go ahead and I'm going to put a resistor here, R, and a resistor here. Make them both the same, R. No, I'll make that R1, R2, but I'm going to ground this one, ground that terminal. And then what I'm going to do is this. I'm going to put a voltage source here plus the minus VI, and I'm going to put a resistor here, R3, then R4, and ground it, and I want to know the output voltage. Let's see how this works. So I want to know this with respect to ground. Now I want you to think through it. You're smart. One thing about, and I'm going to say this, and I hope I don't get in trouble, and if you need to cull this out, do it, but I've always believed this, and I think it's true. I've always believed that engineering is a magnet for the smartest people. Now, pre-med would arguably have as many smart people, but the thing about engineering, it really focuses, it sharpens your reasoning skills. Now, there's very few things do this. Playing chess sharpens your reasoning skills, stuff like this. But in engineering, you're always thinking about how to be clever and yet go through a deductive process. Sometimes you're creative too. I've had many engineering students go into medicine and go to become medical doctors. I had a great friend of mine was Sean Malone. He was a master's student here. He's got his master's here. His father died. Believed he was poor medical care. He decided, and he played football here. He was this big 270, 80-pound guy, about 6'6". And he was brilliant. He was an engineer. And he then decided to be a medical doctor, and it was trivial. Because by that time, all the physics and mathematics is trivial that they have to take MCATs on. He had to take chemistry, and he had to take biochemistry, and he had to take organic chemistry, a few things, and he took MCATs and just killed it. He got in medicine. Now he's an interventional radiologist in Huntsville. Is anybody from Huntsville? You can look up Sean Malone. He's an African American, and he does all sorts of really charitable works. He's huge. His father was a minister, and he died, and so he went into medicine because of that. He would have been a great engineer, but he's a medical doctor. The one thing about medicine is they do make a little bit more money in the beginning, sometimes a lot more money. But engineering is the thing that culls people. You have to be able to remember as well as reason at high levels. You can't get through this major unless you can do both. And I've always believed the smartest people ultimately end up in engineering, some form. And that's just me. So how do we do this problem? Well, what did I tell you? Always find the voltage across one of the inputs, right? Where's the source voltage that's driving this thing? Right here, right? All right, do you agree with me? Now, how much current can flow into that? None, so really what I need is the voltage across that resistor, right? Y'all follow me here? Give me a show of hands if you do. So if I can get the voltage across this, which is simple voltage division, I got the voltage on the plus terminal, right? If I got the voltage on the plus terminal, I have the voltage on the minus terminal, right? Once I have the voltage here, I have the current through there, don't I? See the process? If I have the current there, how much flows out of there? None. Where's it coming from here? Don't I have the voltage here now? Yeah, so that's the thought process. And just for kicks, I'm going to do this. I'm going to put in real values. I've got 5 minutes, and I know I'm talking fast. So I'm going to put in real values. It makes it a little clear sometimes. I'm going to leave this to be 10 volts. And I'm going to make this 5 ohms, make this 5 ohms, all right? Then I'm going to make this resistance, say 10 ohms, and I'm going to make this 100 ohms. All right, and I want to know V out. Let's go through this. I know you guys can do it. You with me? This will make it clear, all right? What's the voltage across the 5 ohm right here, from here to ground? It would be 5 over 5 plus 5, or 1/2, correct? Times 10, or 5 volts. So there's really plus to minus 5 volts there. If I have a different color marker, I'm going to use it. I don't. Just about. Typical. So if I have 5 volts right here, what's the voltage here?
5 volts.
5 volts, right? What's the voltage here? 0, correct, class? Right? Ground is 0, correct? All right, how much current is flowing here? 5 minus 0 divided by 10, or 1/2 amp. Do you all agree with me? Give me a show of hands if you do. All right, do you see it? Gotta make sure everybody sees. So there's 1/2 amp flying through there, 0.5 amps. All right, how much current's flowing here? 0.5 amps, right? What's the voltage across this? 100 divided by 2 is 50. Agreed, class? I'll stop for a second. Catch up with me. Gotta make sure. Does everybody see it? So that's 50 volts across that 100 ohm resistor. That's 50 volts. Now, what's the output voltage? Now this one you be careful on, because you want to just say, oh, it's 50. No, it isn't. What are you going to do? Well, you can start from here if you want, or you can start from here. From here to here, it's an increase of 5. Do you agree? That's ground, that's 0 volts. 5 here, no difference here, right? 5. Then I got an increase of 50, correct? Or the output voltage is 55 volts. Do y'all see what I've done? Can I get a show of hands? Make sure, and I ask this, I know I irritate people, but if I don't see most of the people raise their hands, I know that I'm not getting through to you. So it can gauge me, yeah.
Can you just run through one more time?
Sure. Watch this carefully. Now this is a closed loop right here, right? First, you understand how I got 5 volts here.
Yeah.
Now that 5 volts has to appear here, does it? Now 5 volts is here and there's 0 volts here. The current would be 5 over 10, or 1/2 amp, right? That current can't come from the negative terminal, it has to come from there, right? 1/2 amp times 100 ohms is 50 volts, right? Then the output, you just go through and you get it. Now listen to me carefully. People will memorize formulas. There's all sorts of permutations for how I can put the resistors there. But if you understand the basics, no current in, no voltage across, you can solve any of these problems in a trivial manner. It's not hard to do, but the minute you just try, and people do this to me all the time, they try memorizing every permutation. Where could he put a resistor? Where's the next? And it messes the whole thing up, all right? So here's the next one. I'm gonna get another one in yet. And I'll put it over here. By the way, these are cheap. And one chip may have 10 of them on there. Low frequency, the 741s were the ones I used, but this is just a type of operational amplifier. You can get these, and you can have a ball making things once you really kind of learn a little more electronics and how to build power amplifiers. And the biggest thing with power amplifiers, I'm gonna throw this out here, I might have said this already, is the cost of the transformer. Transformer's a huge chunk of metal. I mean, it's really iron, and it's got laminated iron for the core, but that's the thing. When you get that and you design around it. Now, the nice thing is there's junkyards everywhere. We got a whole bunch of old electronics downstairs, I mean, with huge transformers. And I'm sure you could get, talking to our department chair in a nice way, he would allow you to scavenge one of those things for your own purpose, but you can have a ball with this. I've had one kid in particular, wasn't an E, he was an ME. This kid went overboard. He decided to build speakers, a subwoofer, along with everything. And you all know what a subwoofer? It's basically a standalone bass speaker that really causes the sound to sound. Does anybody own a 5-1 system around here that has a subwoofer? Nobody? Oh, they're amazing. Anyway, it changed. You don't go to movies after you get this. I mean, why bother? It sounds better at home. But I'm going to tell you that you guys are sitting pretty to do this. In another 2 classes, you'll be able to do your own home stereo, home entertainment, everything. All right, here's the deal on this one. Now I'm going to do this. I'm going to put R1 here. I'm going to bring it around. I'm going to put R2 here, right here. Now I'm going to take this and come back this way and put a resistance here and a resistance here. Call this R3, R4 grounded, and one will be a little trickier, but I'm going to show you how to do this. All right, now this one, there is no easy way to get the input voltage. Do you follow me? But I want you to see this, all right? You know one thing for sure, that the input voltage right here would be V out times R, R4 over R4 plus R3. So that is going to be V out times R4 over R4 plus R3. That's the voltage right there. Do you all agree? Because if that's V out, it's just divided down, correct? You all see it there, class? Take a look. If that's V out, right? That's a simple voltage division. No current can flow in or out of that positive terminal. You all see it? All right, now once I have that voltage, what do I have? That voltage right there, don't I? Once I have that voltage, what do I have? I have this current, right? That current would be equal to this voltage divided by R1. Do you follow my thought here? Once I have that current, what do I have? I have that voltage, don't I? And guess what? Once I have that voltage, I set it equal to V naught, right, in this first one, and it solves for the actual value of V out. All right, I'm going to stop there because I think I'm over. Am I over right now? What?
I got you at 10:50.
Okay. I'm trying to, I know you have to go to Parker, and I know probably other people have to scat and run. Did you all understand this stuff?